Welcome to Psychology Hub. At Psychology Hub, we break down the science of the mind, making psychology easy to understand and fun to explore. Whether you're into mental health, behavior, or learning how to think better, we've got you covered. Introduction. Understanding synapses. What's 1,000 times thinner than a sheet of paper, more abundant in you than grains of sand on a beach, and shows how the smallest things can have enormous power? It's the synapse, the critical connection between two neurons. If neurons are the framework of your nervous system, then synapses are what bring that framework to life. Neurons on their own are impressive, but their true strength lies in their connections. Without communication, a single neuron is essentially useless. The term synapse comes from the Greek word meaning to clasp or join. It's a meeting point. When an action potential sends an electrical impulse down an axon, it hits a synapse. This is where the signal is converted into a different form and passed along to another neuron. These connections are remarkable feats of bioelectrical engineering and are staggeringly numerous. Your brain has about 100 billion neurons, each linked by 1,000 to 10,000 synapses. That adds up to 100 to 1,000 trillion synapses. Each synapse acts like a tiny computer, running multiple processes at once and adapting based on neuron firing patterns, strengthening or weakening with use. These are the building blocks of learning and memory, but they also play a role in psychiatric disorders and addiction. Every experience you have, from joy to hunger to confusion, relies on these electrochemical signals in your body's messaging system. Electrical versus chemical synapses. If you've ever texted, you know that good communication means knowing when to send a message to the right group and when to respect boundaries. For instance, sending a group text at dawn about your maple bacon donut might not be ideal unless you have bacon-loving friends. But if Bill Murray shows up to karaoke, that's a perfect moment for a mass text. Neurons communicate in two ways, depending on how quickly the message needs to travel. Some synapses are electrical, like an immediate group text. Others are chemical, slower but more precise and controlled. Fortunately, your nervous system knows exactly when to use each type. How electrical synapses work. Gap junctions. Electrical synapses work by transmitting ion currents directly through tiny channels called gap junctions. These are super fast because the signal stays in its pure electrical form, with no conversion like in chemical synapses. This direct connection allows one neuron to trigger thousands of others in sync, much like how heart muscle cells work together for coordinated speed and strength. However, if all synapses were electrical, your nervous system would become chaotic. If every neuron activated all its neighbors simultaneously, it would be like a never-ending group text, causing overstimulation. That could lead to serious dysfunction. How chemical synapses work. Neurotransmitters. Chemical synapses are more common and precise, using neurotransmitters, chemical signals that travel across the synaptic gap to deliver their message. The big advantage here is control. Chemical synapses allow signals to be modified, amplified, or inhibited right at the synapse. This process has two main components. 1. The presynaptic neuron sends the signal through its axon terminal. 2. The postsynaptic neuron receives it through receptors on its dendrites or cell body. Despite the tiny gap, the synaptic cleft, messages travel through a series of chemical events. Neurotransmitters are released, travel across the gap, and bind to receptors, turning the signal back into electrical form. How neurotransmitters work. When an action potential travels down an axon, it activates sodium and potassium channels in sequence. This eventually triggers voltage-gated calcium channels to open and release calcium ions into the neuron. This flood of calcium causes neurotransmitter-filled vesicles to fuse with the cell membrane, releasing their chemical messengers into the synaptic cleft. These neurotransmitters then bind to receptors on the postsynaptic neuron, resulting in either an excitatory or inhibitory response. Excitatory neurotransmitters make the postsynaptic neuron more likely to fire by making it more positive, depolarization. Inhibitory neurotransmitters have the opposite effect, making the neuron more negative, hyperpolarization, reducing the likelihood of firing. Since a neuron can have hundreds of synapses, the final decision to fire depends on the sum of all the excitatory and inhibitory signals it receives. There are over 100 types of neurotransmitters in your body, each with different roles, affecting everything from movement to mood, sleep, appetite, and alertness. Once neurotransmitters have done their job, they are quickly cleared from the receptor sites. Some are reabsorbed by the presynaptic neuron reuptake, while others are broken down or diffuse away. How cocaine works. Many drugs, legal or illegal, target this neurotransmitter system. Cocaine, for example, affects serotonin, dopamine, and norepinephrine. Serotonin helps regulate mood, appetite, and sleep. Low levels are linked to depression. Dopamine is involved in pleasure and reward, triggering feelings of joy and motivation. Norepinephrine controls the body's stress response, increasing heart rate and preparing muscles for action. When you take cocaine, it blocks the reuptake of these neurotransmitters, especially dopamine. This causes them to build up in the synapses, producing intense euphoria, but also anxiety and overstimulation. However, your body has a limited supply of these neurotransmitters. Repeated cocaine use depletes them and alters the brain, reducing receptors and requiring more of the drug to achieve the same effects. This is how addiction begins. Conclusion. Today, you learned how electrical synapses use ion currents to transmit signals through gap junctions, while chemical synapses convert electrical signals into chemical ones and back again. You also discovered how drugs like cocaine interfere with this delicate system, leading to long-term harm. In their natural state, synapses work with incredible precision, knowing exactly when to excite, inhibit, and communicate. This version keeps the same core content while making slight refinements for flow and readability. Let me know if you'd like any further changes. Thanks for watching.